Hello again, it's Cliff here from Down Under. Well, in this video I'm going to be doing what you could call stacked parts production. That is the fourth axis stacked parts production, where you're making multiple parts automatically at once. A highly efficient process that suits parts of a certain geometry. And these parts are the lathe tool setters, index plates, the level vial index plates, and I need to do a production run of these. Been doing some really interesting production work lately, and there should be lots of videos to follow. Cheers, I'll get on with that. I've been doing a pilot production run of the lathe tool setter electronic version, so that's going to be called LTSE, and also developing a new mechanical lathe tool setter that will be called LTSM, and they both need these level vial index plates. So this video is going to be about producing these index plates on the fourth axis. So it'll be machining using stacked parts or stacking parts on the fourth axis. So a highly productive way of making multiple parts automatically. A low-cost fourth axis like this Tormach Super Spacer can be a very productive kit for certain types of parts that you can stack together and machine several at once. I could stack together 12 or more of these parts, and the machine would run automatically and machine a lot of different features on multiple sides. So you can see here it's a very efficient way to machine something automatically. I'll go through the setup now. Stage one is pretty simple. I just bandsaw out the 6061 aluminium, fly cut it, vice size pieces to thickness and width, finished width, and then set it up in the mill, interpolate out the holes and precision bore them and chamfer them. Then I can just saw off the little billets into the length with a little bit extra on for the fourth axis stage. So 3 cuts to zip them off in the bandsaw, so they're finished in one direction across flats and rough bandsawed in the other direction across flats. Okay, machining these level index plates on the fourth axis, let's go through that. Now, there's just a mechanical setup to start with. I won't go into it in great detail because I've done another video called Fourth Axis Setup and Run where I go into it in detail. But just roughly, I mount the dividing head on the table with that very slim profile bolt under there, and one I drilled and tapped in the middle there. That allows the dividing head to fit snugly right on the end. I used an ER32 collet flanged holder and clamped up very tightly on a 3/4 inch mandrel, which has a 3/4 inch thread on the mandrel with a center in the end. Now I have a tailstock for my other dividing head, which has a very low profile, and I just extended it up to the right Z height, and that's a very efficient low profile dividing head. Now I'm going to put the parts on there, get them in the right rotary position, and run the NC program. And so I'm on A0, and you don't have to worry about the backlash so much if you always command your fourth axis to rotate in the same direction. So I'm going numerically to 0 to 90 to 4. I want to go the other way. I'll command it GOA -1 and then GOA 0 to take the backlash out. So I'm always going in the same direction. So here I'm sliding on the parts got a machined washer against the chuck there. I've got these adjustable parallels, two at the same height, locating on the machined flats on the parts to get it in the correct rotational position. Putting on the nut and the washer, I'll slide the tailstock center into contact and then tighten up that bolt. That'll give a clamping frictional face clamp on all the parts so they don't turn when I'm doing the machining. So the order of tightening is, and I hope this will work out okay, is that the mandrel has not got a step on it or a flange on it to save time. It's just a plain mandrel gripped tightly in the collet, but the tailstock is tightened up against the end of it to take some of the thrust, and when I tighten up this nut, there's a combination of the tailstock and the collet holding the mandrel in place, and I can tighten it up to get the clamp tension on the nut, and hopefully nothing will move lengthwise or in a rotational position if I get that correct. And of course, what video would be complete without showing setting the work offsets with the Tormach ITTP. So my first tool is just a fly cutter made out of high grade, high cobalt, high speed steel. It seems to last pretty well in aluminium, and it's easy to sharpen it with a diamond lap. So the first bit of the tool path should be to rotate the fourth axis 90 degrees to the bandsawed surface, and then take a series of facing passes to face that side down to finish size. Then lift the tool up and rotate from there another 180 degrees for the other side. So now the fly cutter has cut the flats and the corners, and the next tool change is a 3/8 bullnose cutter to cut the grooves for the index bubble vials. And the next tool change is a slot drill to counterbore for the cap screw, and then I'll put in some drills to drill the tapping and clearance sizes. The next tool is a stub drill. Well, I think they're okay. Nice and square. Nothing seems to have moved. That was my only concern, that it would shift under the load of machining, because I cut the corner and just made a basic mandrel without a flange or shoulder. Well, I won't go into the CAD CAM side of it too much because I'm using CAD CAM, and I know a lot of you will be using other CAD CAM software. But just in simple terms, you're just producing some simple 2 and 2.5D toolpath. For example, facing toolpath for the fly cutter, and profiling toolpath for the ball nose cutter, and drilling toolpath for the drills and so on. And then you can produce more than one set of that code, stack it all together, and then open it up in your machine and just manually edit in some fourth axis moves, some A moves. Okay, so we've produced the G-code, we've put it into the machine controller, into Path Pilot. I'll just go through this really quickly because a lot of you will know this. So there's a bit of facing toolpath, for example. So we'll just open that up in Edit, and then right at the top we'll put in, where are we here, a clearance move, a GOA90, that's rotating it so that the flats are in the right orientation. It'll run that bit of code. Another clearance move, GOZ40, and then GOA270, that's an additional 180 degree rotation, and we'll run the second part of the code. And then you can just copy and paste. So it's a good idea to run those individual little tool paths initially, just to prove your first part. Then you can copy paste them together into one big program. Now you can also do this with subroutines, but because this part, each face has got a slightly different tool path, because the part is rectangular and not square, and there's holes on some faces and not others. It's easier for me to have individual tool paths with those differences and then just stitch them together. I've been quite nervous that the parts would turn on the mandrel because I couldn't get enough clamping pressure. It's a bit Mickey Mouse what I've done. It's just held in the collet. I did that so I could pull it out and have different lengths, and also to save time. Machining it with a shoulder would take a lot longer. But in a way, I suppose it works, because when it's tightened, it actually pushes on the collet, which is very slightly proud, and so the more I tighten the nut, the more it pushes the collet into the taper. So it's a sort of safety self-tightening thing, more by luck than good management. It actually amazed me that it didn't come loose, but now I can see why it hasn't. No, it's not worth the stress. You know, it's spoiling the fun of the job, being slightly anxious about it suddenly letting go. For the sake of half an hour's work, I just pinned the collar on there, which I can reposition if I do a bigger stack in the future. So that's just going to take the stress off me now. It's quite funny really, that whole question of will the part hold or will it let go? What's the clamping force of the nut against the collet? That Mickey Mouse setup I had in the beginning. You know, do you do this? Do you draw a graph of it? I quite often imagine a graph in my head. You know, along here you've got each successive run, and vertically you've got the breakaway point. At that point, let's say that's 80 Newton meters. It'll let go at that point. And with a sharp cutter, the first run when you're fly cutting, it gets to there, it's quite safe. But it's getting a little bit duller on the second part and a little bit closer on the third, and I'm starting to get really nervous, and I'm sort of imagining it graphically like that. Do you do that? So now I've got the collar and a much more secure system. I've lifted it up here to about 200 Newton meters, and I've got a long gap there, a margin of safety. Crazy how the brain works when you're stressed. And finally, a simple finishing operation, taking it from the machine part to a finished part. This video is a bit long for me to go into that, so keep your eye out. I'll produce a short video on this subject, just covering finishing of parts.